Okay, so today is kind of part two of my thinking and interest lately in delays and asynchronies in ecosystems. And unlike yesterday's talk on wild rice, where the idea of delay and asynchrony was, we built it into the research right away. That was the core part of my hypothesis. In this research here, it wasn't until we were pretty far along in the research and trying to figure out why this model that I'll present here was working the way it was, that we realized that there are implicit built-in delays in the model that result also in some complex behaviors. So it was kind of if anything, even spurred me more on to think about delays and asynchronies in ecosystems and what's going on here. The fact that these two completely independent lines of investigation are kind of leading to the same place here. This work, actually, Angela Sharp is in the math department, and she teaches a course that we developed in kind of a calculus for natural sciences, it's called, or calculus for biologists class, and as an alternative to Calc 1. And it's just as rigorous as Calc 1 is, but if anybody's taken the traditional Calc 1, you know that the equations are things of interest to engineers and physicists, like a pendulum and a spring, but things not normally found in organisms. And so she developed another course, and we worked on it together, Calculus for Biologists, and it's just been a lot of fun working with her on various things over the years. But this particular project was actually inspired by an undergraduate who had taken both her course and then took, a number of years later, my subsequent course in mathematical ecology as a senior. It's a graduate course, but he took it as a senior. And he came to us and said he wanted to do an independent research with us on modeling wildlife diseases. So I didn't know anything about modeling wildlife diseases, neither did Angela, so we thought, well, this is a great way to learn. We have a student help us. So we worked through some of the examples in Bob May and Roy Anderson's book and a few other things. And actually, if you really want to know about this, I think the best book is a book by Rohani and Keeling called Modeling Wildlife Diseases, I think it's called. That's the book that you really want to read on this. And then as we went through this, since he was a deer hunter, he says, well, what about chronic wasting disease? So we started reading up about it, and we're very confused about a lot of things until we read this paper by Miller and Hobbs and Taverner, which really was an eye-opener to us. So what I'm going to be talking about is some modifications we made to their model, which is a really great model, and some surprises that have come out of this. So this is not, disease modeling is not really my field. This is just sort of a side track here. Okay, so we saw all that already. Okay, so some of this I'm going to be preaching to the choir. Actually, I'm a little trepidatious coming to CSU, like one of the powerhouses of research in chronic wasting disease, and giving a talk. But chronic wasting disease affects deer and elk. I thought possibly moose, but conversations with Tom Hobbs yesterday, he said, no, there's been some confirmed cases of chronic wasting disease in moose. It's a spongiform encephalopathy. In other words, it's a prion that turns the brains of these animals into Swiss cheese, just decomposes the brain. It's similar to mad cow and cattle, scapies and sheep. And actually, scapies is a big problem in Iceland with the sheep. And I'm hoping, if anything, that out of this research, I could get an invitation to go to Iceland out of this. So that's my main motivation for doing this research. And Jakob Creutzfeldt disease in humans. Again, it's caused by prions, misfolded proteins, which can enter cells and control cells to reproduce themselves. So one of the interesting things about this is it's actually led me to reading about the thermodynamics of folding in proteins and the biochemistry of it, which is a cutting-edge, rapidly developing area in biochemistry, in which I find absolutely fascinating. One of the things I love about ecology is you just don't know where it's going to lead you. And it leads you to so many different things if you want to understand things. And I never thought as an ecologist that I would become fascinated with the thermodynamics of protein folding, but it really is quite interesting. This is from a great review paper that was in Science 4 years ago. It's a short review paper, but it really gets at the meat of it. So if you're interested in protein folding, I'd highly recommend this paper by Service. And what this is a schematic of a surface of free energy on a protein. And as the protein starts to fold up by formation of thiol bonds between sulfur linkages, hydrogen bonds between sulfurs, the free energy declines, and it follows a pathway down here, eventually getting into minimizing free energy to N. That's not north, but it's native configuration here. But along the way, for reasons that are not quite known, occasionally, it could even just be stochastic quantum fluctuations. The protein gets diverted into a local well here, and once it gets into a local free energy here, it can't pop out of that well and come back down over here. And those proteins are then misfolded. And the vast majority of these things, cells don't recognize them, they do nothing, they're neutral, or they get shunted into vacuoles, or the immune system grabs them and puts them away, or they get voided out of the animal or whatever. But occasionally you get these prions, which can, in ways that are still not quite biochemically clear, re-enter a cell and begin to redirect the machinery of that cell to reproduce more copies of the prion. So the biochemistry of all this is very, very fascinating. Here's the known distribution of chronic wasting disease in yellow here. The W is where it was found in wild herds, and C is in captive herds. We've had one incidence in Minnesota here, actually on a game farm, south of Minneapolis. Actually, this isn't quite in the right place. It's more down over here. And just the other day, they found a doe with dead doe with chronic wasting disease in northwestern Wisconsin, right over here, right across from Duluth, where I live, right on the corner of Lake Superior there. So it almost certainly is throughout Minnesota here in wild herds too. We just haven't seen it yet. But the big hot spot is right along here in the front range of the Rocky Mountains, and of course that's why it's of concern to people here and in Wyoming and New Mexico. Here's the Miller, Hobbs, and Tavener model, which was published in Ecological Applications in 2006. And actually in that paper, there were a series of models that Tom and his associates did a really wonderful job. One of the things I like about Tom's research is that he treats parameter estimation as a hypothesis to choose between different models. So if you want to learn about these techniques of how you choose between different models by using the proper set of parameters, this is a great paper to read. So we read the paper, and this was the model that turned out seemed to give the best fit to the data. So there's the herd is divided up, well, the model is divided up into 3 pools: a pool of susceptible deer population, an infected population here, and this environmental pool of prions that are in the soil. And I'll get more to that later on at the end of the talk, but the prions are stabilized to some extent when they get into the soil. And there may be some reinfection directly from the infected animal back to susceptible, healthy animals, but for the most part, the susceptible animals are reinfected by ingesting soil or prions from the environment, and then they get infected like this, and the infected animals die. So M is the ordinary mortality due to hunting and roadkill and predators and everything else. There's a transfer rate here, gamma, which depends on the product between S and E, this size of this pool and this pool. And that product is basically proportional to the probability that a susceptible animal will actually ingest some of the environmental pool. You might recognize this as like in the Lotka-Volterra predator-prey equations, that this is kind of the form, the simplest predator-prey equation of an interaction. So the susceptible gets transferred to infected, and the infected die at this background mortality rate plus an additional mortality rate due to the disease itself, which is quite high. Before that happens, they transfer through voiding or even through their carcass a certain amount of the prion from here to the environmental pool at a rate tau. And then there's an output from the environmental, the prion from the environmental pool at a rate tau. That could either be, or this is epsilon, that's tau. That could either be leaching from the soil or just degradation of the prion in the soil by bacteria. So this was an interesting model that came out of it, but we weren't kind of too satisfied with this constant birth term here. And this is not a constant per capita birth rate, it's a constant number of births that are, the deer give rise to each year. In human disease models, typically what you have is 3 pools, a susceptible, infected, and a recovered pool. Well, nothing recovers from chronic wasting disease, so the recovered pool here is actually replaced by an environmental pool, and having a constant birth term is typical in human disease models. And the reason for that is human birth rates change over a decadal time period, but most human diseases like measles or flu or something like that go through a population of human beings in a few months. So during the time scale of the disease going through the population, the birth rate doesn't change. And to simplify things mathematically, most human disease modelers just treat birth rate as a constant. Well, I didn't like that. I mean, the model was interesting. I didn't like that. So one day we just said, you know, let's just replace that with the logistic function, because that's the function usually used for the growth of this population without any disease. So that's what we did. So we have a logistic function here coming back in and just regenerating this. And notice what we did, we also removed this mortality term here from the susceptible pool, because density-dependent mortality is subsumed in the logistic function here. Actually, it doesn't matter if we kept it in here, the qualitative behavior of the model is the same. We could even take this mortality term out of here. The key thing is the mortality due to the infection here. So either way, the qualitative behavior of the model doesn't change. So this seemed a little more interesting to us, because the lifetime of chronic wasting disease in the soil can be anywhere from 3 to 15 years, and in 3 to 15 years, we're going to get density-dependent self-regulation of the deer population. So unlike human beings, where the birth rate changes in a much, much slower time scale than the disease going through the population, in wild populations, the growth of the population per capita growth rate changes on the same time scale that the disease is active, at least for the chronic wasting disease. So what we have to do is consider both the lifetime of the prion in the soil here, which is actually 1 over tau at equilibrium. 1 over tau is the lifetime, as well as the density-dependent dynamics depicted by the logistic equation up here. Now, I want to warn you, this talk is going to be a lot more mathematical than yesterday, and I'll try to go through it as if I was giving a lecture to my class on this in detail. Don't get hung up on the mathematics. Try and keep focused, and I'll try and keep focused on the biological message behind the mathematics. But if you can understand even a little bit about the mathematics, I think it amplifies some of the biological message. And actually, the surprises we discovered really were we didn't suspect them before we went through the mathematics here. Okay, so that's a cartoon. Some people call this a model. To me, this is a cartoon. A model is a set of equations that we want to turn this into. And the nice thing about these cartoons is you have 3 boxes, you need 3 equations. 1 equation for the rate of change of this, and this. So we're going to have 3 differential equations, ds dt, di dt, and de dt. And basically, to write the equation, you take all the inputs going into the model, and you subtract all the outputs coming out. So for each box, you look at all the arrows coming in, you take each of the terms associated with that arrow coming in, add them all up, and you take each of the terms associated with the arrow going out, and you subtract them. And there's a set of equations. So there's the model. So constructing a model actually is not too difficult. It's analyzing the model that is difficult. So here's the rate of change of the susceptible, infected, and environmental pool over time. You see here's the logistic equation for the input, minus gamma SE for the output. That output there becomes the input to the infected pool. So the input to the infected pool is not controlled by an interaction between infected and susceptible. It's controlled by an interaction between environmental and susceptible at a per capita rate gamma. Here's the mortality rate there. And here's the transfer rate from the infected pool to the environmental pool at a rate epsilon. And here's the loss rate of the prion from the environmental pool there. So just inputs, outputs. Like I was talking about yesterday, mass balance. But it's mass balance on a population of inputs and outputs, births and deaths. Same thing. So what we usually do with these models first is to find what are the equilibrium solutions. And the equilibrium solutions are the values of S, I, and E, in which the rate of change of each of these all of these simultaneously is 0. Now, certain people say, why do you guys bother with equilibrium solutions? Nothing is at an equilibrium. It doesn't mean anything. Nature is never at an equilibrium. Well, we do for two reasons. Number one, it's the easiest thing to do first to understand how the model is working. But number two, things may never in nature be at an equilibrium, but they're either moving towards an equilibrium or they're moving away from an equilibrium. And what most experimental people want to know is, how are they moving towards an equilibrium or away from an equilibrium? And that's a transient response. That's harder to do. But lots of times if you examine the equilibrium themselves, you'll get at least a qualitative idea of what direction the system is moving and how it's moving away from it or towards the equilibrium. Is it moving towards or away from the equilibrium in a direct path, or is it moving towards or away from the equilibrium in a more convoluted path? If we start with just analyzing what the equilibrium solutions are and what's controlling the equilibrium solutions, and when do you get one and when do you get another, it gives you a pretty good qualitative feel for what's going on in the system without knowing the transient response. So equilibrium solutions are still important things to think about and focus on, even though I admit nature is rarely at an equilibrium. So we actually have three sets of S, I, and E, three values for it, that if you inserted those values, you will get ds dt, di dt, and dt simultaneously equal to 0. And that's what we mean by an equilibrium, that the rate of change of all the pools simultaneously is 0. So the first one is what I like to call the no-life solution. Just there's no deer, either susceptible or infected, no prions, no life. You can see that if you inserted 0 here, 0 here, 0 here, 0 here, 0 here, and 0 here, obviously you're going to get 0 over there. So that's kind of a trivial solution mathematically. What it really means is extinction. And what you want is a model in which extinction is not stable. Okay? So that's one solution. Another set of values for S, I, and K, and the asterisk is the traditional way of indicating that's the equilibrium value of these things, where the deer, healthy deer that are susceptible are at their carrying capacity, and there's no infected deer and no prion in the environment. That's the no disease solution. A third solution is these big complicated solutions here in which you can see the disease is persisting. So you have the susceptible pool at its equilibrium at this combination of parameters. The infected deer are at this combination of parameters, and the environmental pool are at this combination of parameters. And if you actually back inserted those into those equations and go through all the gory algebra, everything's going to cancel and the rates are going to all be 0. So an interesting way to proceed here is, this is the solution that we want, right? Healthy deer and no disease. But look, given a certain combination of these parameters here, we might actually get this solution where the disease persists. So what we want to know is what combination of parameters over here gives you this solution as opposed to this solution. So you could think of these solutions to the equations as being three different kinds of communities. No deer, healthy deer, and diseased deer. Okay? Three different systems that are out there. And what we want to know is what separates this from this. Well, for the disease to persist, or for the deer to coexist with the disease, all of these solutions on this side have to be positive, right? Well, this one is already positive because all of these parameters have positive values, so that one's already positive. These two are positive when the numerator is positive, so we set the numerators of both of these things greater than 0, and now we can solve for one of these parameters here in terms of all the others. And that's a critical value of that parameter. That parameter has to be greater than some expression which is a combination of the rest in order for the disease to invade. And if you look carefully at it, really what it amounts to is it's really what's in brackets here. All you have to do is set what's in brackets greater than 0. So this actually becomes easy to do by hand. You just set it greater or equal to 0 and solve for one thing. So let's solve for carrying capacity and see what happens here. Is there a critical carrying capacity that if we exceed it, the disease might invade the herd and persist, and if carrying capacity is below that, you're going to get this solution right over here instead, be stable. So when we basically set this here, the term in brackets in the numerator greater than 0, we get this critical carrying capacity in terms of all of the others. Okay, so there's a critical carrying capacity there. But notice a strange thing. That critical carrying capacity is equal to the equilibrium size of the susceptible deer herd. See that? Oop, hold on a second. There. That turns out to be my critical carrying capacity. So what's going on? That seems a little strange. What's going on there? So why does that equal the equilibrium size of the susceptible deer herd? It seems like a mathematical question, but actually figuring that out gave us a lot of biological insight into what's going on here. So to do that, what we want to do is we have a model that's basically in 3 dimensions here, as mathematicians like to say. You have 1 dimension for susceptible, infected, and the environmental pool. Well, the expression for the environmental pool, this is a nice linear term here, and we can easily reduce that and get rid of that. What we do is we set this equal to 0, solve for E, and get that expression, which you could see is going to be equal to epsilon E over tau, and then we substitute epsilon E over tau for E wherever we see it up here. Technically, that's called the quasi-equilibrium solution, but it's a nice, easy way to proceed. What we've done then is reduce the problem from 3 dimensions to 2 dimensions. So now automatically it's easier, because we only have to deal with S and I to figure out what's going on, not all 3 of these things. What that allows us to do is to construct null-clines in a plane. Before, we'd have to construct null planes in a 3-dimensional volume, which is hard to figure out what's going on there. So these null-clines, if you're not familiar with them, what they are lines. Well, the plane is, on this axis, we have the infected pool in number per 100 square kilometers, and on this axis of the plane, we have the susceptible pool in number per 100 square kilometers. And these lines here, this vertical line is the null-cline. A null-cline is where the rate of change of a particular pool is 0. So here's the number here, or the line here, the null-cline here, where the rate of change of the infected pool is 0. It's 0 everywhere along that line. And the null-cline for I equals 0 is S equals this, which is the K-critical term. So this line intersects the susceptible axis at K-critical. K-critical is right there at that intersection point. Okay? These other nullines are where the susceptible, rate of change of the susceptible pool is also 0, and that turns out to be this term here, and you can see if you multiply through it like that, that's just a straight line. I equals AX minus S, or A minus BS, okay, over here. So this line here intersects the S-axis, the x-axis, or the axis here, the S-axis. At that point, the infected pool is 0. So any place where this intersects the S-axis, that's where S equals K because I equals 0. So these big dots here are where the equilibrium are. The equilibria for the two things together are where the two nullines intersect each other because that's where the rate of change of S is 0 and the rate of change of I is 0. If it's a filled in dot, it's a stable equilibrium. If it's an open dot, it's an unstable equilibrium. And the system always moves towards stable equilibria and away from unstable equilibria. Okay? So let's see what happens here as we increase K. So here's K critical. Here's a value of K equal to 2. That's along here. And you can see there's two equilibria. One, I equals 0 and S equals K. The other is in the fourth quadrant with negative infected populations, which is not biologically reasonable, but it's mathematically interesting. And one of the things I've learned is you have to pay attention to all of the solutions because even if they're not biologically reasonable, they do give you some insight into what is going on with the other ones. So what happens if we increase the carrying capacity here from 2 to higher levels? Well, what happens if we increase K? This is going to move over, and that slope of that line is going to get flatter and flatter. See that? If I increase K, I'm just pulling that nullline that way. Okay? When I do that, this equilibrium moves this way, this equilibrium moves up, and when K equals K critical, they both collide. And if I keep pulling it that way, now I have carrying capacity greater than K critical. This equilibrium continues to move up. Any coexistence equilibrium has to lie along that line, and at this point they exchange stabilities. And now the coexistence equilibrium with the disease persisting becomes stable, and the deer alone without the disease at carrying capacity becomes unstable. And what that's called mathematically is a transcritical bifurcation. So when K is greater than K critical, the disease invades and persists. If we keep pulling this out more, you see this little circle around this one? All of a sudden now that becomes unstable, and what we have is some very interesting things happening here. So this is a simulation of what happens with K equals 2, 12, or 34. And I think for this simulation, we used a output rate of prions from the soil of 1/3 per year. Tau is 1/3. So the inverse of that, remember, is the retention time of the prions in soil. It's 3 years retention time in the soil. I'll show you what happens when we vary tau in a minute. When K equals 2, which was less than that critical carrying capacity, which for the parameter values from the Miller, Hobbs, and Taverner paper and a carrying capacity of 2, remember in this model, that's where the disease does not persist, and we get a disease-free herd. And what happens is the big heavy bar is the susceptible population, the light bar is the infected, and the dotted one is the environmental pool. So the infected and the environmental, we start out with a little bit of those, but they go extinct. And here we have a nice, stable, healthy deer herd right at the carrying capacity of 2. See right there, there's a K of 5, 10, 15, 20, and that's right at 2. Okay? When we increase it above the critical K to 12, oh, look what's happening now. Both the susceptible herd and the infected herd come to a new equilibrium, but they're coexisting, and here's the environmental pool down here, and there's a little bit of a wobble, a damped oscillation as you get here. but they both come to an equilibrium, so the disease is persisting. If we make K really high, and incidentally, the units on these K is number of deer per 100 square kilometers. So 34 deer per 100 square kilometers, look what's happening. Looks like we have a stable limit cycle and recurrent epidemics in the deer population at a high carrying capacity. So this looks an awful lot like a well-known behavior of one of the predator-prey models that Mike Rosenzweig came up with called the paradox of enrichment. And in this predator-prey model, Mike Rosenzweig noticed that as carrying capacity increased, the predator can first invade and form a stable coexistence with the prey, which is a transcritical bifurcation exactly like we saw with the disease. And as K increases further, the coexistence equilibrium becomes unstable, and we get a stable limit cycle surrounding the coexistence equilibrium. And at that point, that's known as a hop bifurcation. So many of you might be familiar with the bifurcation in the logistic equation where you get the period doubling bifurcation. That's the one that's in all the textbooks, and it's only in the textbooks because two things. It leads to chaos, which is interesting, but it's really the first one that ecologists and biologists started paying attention to. But in most ecological models, these are the two really important bifurcations that happen. Things either get to invade, and actually this is what you want to look for if you're dealing with an invasive species model. You want to deal with a set of life history, find a set of life history parameters and environmental parameters that allows the invasive species to invade and stably remain there. So I think transcritical bifurcations are going to become really an important tool in a lot of ecological modeling as time goes on. But this is the real interesting one where you get the coexistence equilibrium becomes unstable and you get this limit cycle, just like a predator-prey cycle in the textbooks. And here's a numerical depiction of that. Here's the trajectory in a phase plane. Here's the infected pool size, the number of deer per 100 square kilometers. Here's the susceptible pool size and number per 100 square kilometers. There's the coexistence equilibrium, which is now unstable. And if we just perturb away from that and we start with initial values here, they don't return to it, which is what they would do if it was stable. They spiral out away from that, eventually converging on this limit cycle here. If we start outside the limit cycle here for our initial conditions, they converge inward like that. So that's pretty good numerical evidence for a stable limit cycle here. The limit cycle is what's stable because if you perturb away from the cycle itself, things will converge back to it. So that's what's stable. It's not the point that's stable, it's the cycle itself that's stable. And so that's what's meant by a stable limit cycle. So that's interesting because it suggests that the disease is behaving in some way like a predator in a predator-prey model. And a number of people have pointed this out who do disease modeling in wildlife populations, that we could kind of think of disease as a kind of predator on the prey. So one of the causes of the hop bifurcation and stable limit cycle is the addition of the logistic equation for growth of a susceptible population. Without that, if we go back to a constant birth rate, we never saw a limit cycle in any runs we did of the original Miller et al. Model. And I think you could prove mathematically that that model does not have a stable limit cycle. But the other thing is that, and here's where delays come in, trying to think about this, there's that delay in the transfer of prion from the infected population to the environmental pools before transmission in the susceptible population is also needed to destabilize things and cause the limit cycle. And the reason is the limit cycles disappear if we remove that environmental pool and just have direct transmission from the affected back to the susceptible populations. And let me show you that here. So here's what I did. We just removed the environmental pool here, and here we have the logistic growth term here. Now the transfer from susceptible infected depends on the size of the infected pool right here. So the product of S and I gives the probability that the disease, the prion, will be transferred from the infected animals back to the susceptible animals, and that'll cause susceptible populations to go here. Once they get here, they just die from that point. This does not have a stable limit cycle. So there's the equations for that model over here. The eigenvalues of this model here, if one way we can tell if you have a hot bifurcation is, what you do is you solve for the eigenvalues here, and the eigenvalues, they're all, they're complex, but the real part of the eigenvalue here is always negative, and to get a hot bifurcation, what you have to have is a positive real part of the eigenvalue. Okay, that's just mathematics. Don't worry about that. But the point is that you can prove algebraically that in no case here does this model here have any kind of stable limit cycle, because these eigenvalues will always be negative. Each one of these parameters is positive, and there's a negative sign out there. It'll always be negative. It could never go positive. And here's an example of that, a simulation. Again, at that same high K of 34 animals per 100 square kilometers. And if we start out here, what happens in, it just spirals in like this back down to the equilibrium right over there. And it doesn't matter where we start. It's always going to go spiral into that equilibrium. So the stable limits cycles are not possible in this model solely with direct transmission back. It's only because of that environmental pool going back. And actually, if we included direct transmission from the infected to the susceptible pool along with the environmental pool, we still get a stable limit cycle. So the stable limit cycle is caused by a combination of both the logistic equation and the delay in the transfer of that prion from the infected to the environment back to the susceptible pool. So that's for K, but we can solve for any one of these parameters or any combination of these parameters to get critical values for any of these other things that will give us disease persistence or stable limit cycles. So we looked at K, which kind of controls the input of animals into the population. Either K or R, it doesn't matter. Either one is going to give the same thing. Let's look at what controls the output of the prion from the system, which is tau. And in fact, let's solve for a combination of K and tau together that will give us critical combinations of both for no disease, disease persistence, and limit cycles. And that's what this graph here is. So here we have tau over on this axis, carrying capacity over on this axis. So this is increased carrying capacity. Tau is the export rate of prions from the soil. Going in the opposite direction is increased retention of prions in the soil. So as the export rate goes up, retention goes down. As the export rate goes down, retention of prions in the soil goes up. And remember, retention is the inverse of this. So an export rate of 0.5 is a retention rate of 2 years, okay? Or a retention time of 2 years. So these lines here are critical combinations of tau and K that divide this plane up into this region over here where the disease dies off and you just get a healthy deer herd. Over here, the disease persists, but we don't have a stable limit cycle. And over here, you get limit cycles. So let's look what's happening here. Let's take horizontal slices from at a fixed value of tau, the export rate, through here and see what's happening. So when tau is high and the lifetime of the prion, or retention of prion in the soil is short, you reach these critical Ks at very high values of K. For here, K has to get up to close to 20 before the disease persists, or it's got to get way out here somewhere before you get limit cycles. As we decrease tau or increase retention of the soil, prion in the soil, we hit those critical carrying capacities much sooner. So as the prion is retained in the soil, you actually enter into disease persistence much more quickly with any increase in carrying capacity. And that's a little scary. So what is the mechanism controlling the retention of the prion in the soil. Well, this is a cutting edge area of a lot of work. What's of interest to me as my background as an undergraduate and as a beginning graduate student for my master's degree was actually in geology. And one of the things I was doing for my master's degree was analyzing the mineralogy of clays from soils in Antarctica as an index of weathering rate. And one of the clays we were interested in a lot is montmorillonite. And montmorillonite, these layered silicate clays, which are actually derived largely from weathering of micas, this is the mineralogy of them. And what you have here are two layers of silica tetrahedra. The yellow is the silica atom, and around there are 3 oxygen atoms there and 1 oxygen atom here. So you see you've got 2 layers of silica tetrahedra pointing to each other and sharing those oxygens with what's called an octahedral layer in between them. And at the center of the octahedral layer are things like aluminum or iron or other things like that. So you get this, it's called the 2-1 layer clay, 2 layers of silica and 1 octahedral layer. And here you have another down here. And because of charge polarities between these two, things can get in the middle, and this is called the interlayer space here. This is where cation exchange capacity of soils arises. It arises from calcium and potassium and so forth being able to get exchanged in and out of here. So if you had heard of cation exchange capacity, which is a big part of soil fertility, it's because of this. Well, montmorillonite is very interesting. When originally the mineral is a mica, these things are very close together. In fact, they're within 10 angstroms from here to here. And if you X-ray clays, that's what you find out. You find out the thickness of this spacing on the clays. As the clays weather, these charges, this interlayer here becomes looser and looser. Eventually you weather to montmorillonite. And one of the ways you identify montmorillonite is you take the clay and you soak it in some reasonably high molecular weight organic molecule. Glycerol is the typical one. And the organic molecule will get in here and it'll expand the montmorillonite to 17 angstroms. So if you're X-raying the clays, if you get expansion of the clay to 17 angstroms upon insertion of glycerin, you know you have montmorillonite. Okay, so this has taken me all the way back to my geology roots here, which is really kind of cool. I haven't thought about montmorillonite in 2.5 decades. It's been a long time. Well, not only can glycerol get in there, but the prion can get in there, or that's what it's thought. There's been other studies that have shown that the lifetime of prion in the soil is increased with increased amounts of montmorillonite in the soil. Or even if the prion can't get wholly in there, at least part of it gets in there, and it's at least partially shielded from microbial decay in the soil. So the clays, particularly montmorillonite, are shielding in the soil the prion and may account to some extent for the lifetime of prions in the soil. Well, if you look at the distribution of montmorillonite on soils in the United States in purple here, you can see this area here is this big area here right in front of the Front Range where you have a lot of chronic wasting disease. Now, we have a lot of montmorillonite-rich soils in Texas, and chronic wasting disease hasn't been reported there yet. And we have some states out east and even Minnesota, very low montmorillonite Minnesota soils or Wisconsin soils, and we do have chronic wasting disease there. So it's not a necessary condition, or probably not even a sufficient condition, but there's a correlation there and there's a good mechanism for the two. The montmorillonite around here comes from a lot of late Jurassic formations like the Morrison Formation, or early Cretaceous formations like the Mowry Shale, a lot of which you find in the Bighorn Basin in Wyoming. So there's a lot of late Cretaceous, early Cretaceous, late Jurassic formations around the Front Range here and in the intermountain areas here that are montmorillonite rich. And so it may be that the montmorillonites in the soil here may be contributing something to, and I don't know this for sure, it's just an idea I'm throwing out, to the apparent high incidence of chronic wasting disease in the area. So this is the part where wildlife managers don't like to hear this. Increasing carrying capacity above a critical level seems to allow the disease to invade and even persist. What are we doing in wildlife management? What has always, always, always been the goal? Increase carrying capacity. Modify the habitat and increase carrying capacity, and you'll have a bigger herd. Even in conservation biology, although conservation biologists don't use the term carrying capacity all that much, still, what you want to do to conserve rare species is make sure there's enough habitat, which essentially, and good quality habitat, which is essentially increasing carrying capacity. So as we've increased carrying capacity for deer, either intentionally through habitat modification or unintentionally by reducing predators, clearing land, creating suburbia, which is deer heaven, we maybe have pushed our carrying capacities above that critical level. And in the model I showed before, the critical carrying capacity with a 3-year retention time of prions in soil, which is a pretty low retention, lifetime prions in soil, is something like 3 or 4 deer per 100 square kilometers. There are a number of websites that you could look at that give current deer densities by county for east of the Rocky Mountains. They're all above that, all of them. So what the model is suggesting is every deer herd east of the Rocky Mountains is susceptible to permanent invasion of chronic wasting disease because of the high carrying capacity. So that's a conundrum facing us as managers, or anybody as managers. What do I do? Do I keep increasing carrying capacity, but then the disease might invade? And now I may be dealing with diseased herds. Now the disease might be very low, you might be able to ignore it, but politically, I've got to tell you right now, the state of Minnesota is going bonkers over 1 dead deer with chronic wasting disease. Politically, it's a very, very difficult thing to deal with. It's probably more difficult to deal with it politically than biologically. Okay? But if we keep increasing carrying capacity, the model suggests that the deer population is destabilized, and now we get a stable limit cycle, which implies recurrent epidemics. And these critical carrying capacities depend on the export rate of prion from the soil, which may imply a role, at least a partial role, of soil mineralogy into the whole thing. So the cool thing about this problem to me was it made me start thinking about the biochemistry and thermodynamics of protein folding, but thinking about it as an ecologist. And it also made me go back to my roots as a geologist and start thinking about soil mineralogy all over again. And so the neat thing about these new areas, that whenever a field moves into a new area, there's going to be a lot of surprises, and you're going to have to draw on lots and lots of other areas to try and understand what's going on here. And this is a really exciting part of ecology now, because it draws on biochemistry, animal physiology, basic population ecology and management, but also the underlying geology of the landscape and what is happening in the soils too. So wildlife managers are going to have to pay attention to soils and biochemistry, as well as just population dynamics, to really understand what's going on here with their deer herds, or any animal herd, say, or sheep, or cow, or whatever, which is a good thing. It expands our minds and keeps us on our toes. So Harlan Stetch and Bruce Peckham are 2 colleagues of ours in the math department, and they gave us a lot of good advice and just bouncing ideas off of. But the thing I'm most proud of is no taxpayer funds were used in this research. We did this all on our lunch hour. Didn't have a grant or anything. We just got together over lunch, did some things, and gave each other homework assignments for the week, and met the following week and said, okay, what did you find? What did I find? And kept moving along. And that's the way we're going to continue to pursue this. So you can do research without a grant. It's possible. Okay? As long as you got someone else paying your salary. Okay, I'd be happy to answer any questions. But before I do, I really do want to thank everybody once again for your wonderful hospitality. I had a great time talking with everybody. I had a great time talking with the students today. And this is a very, very exciting program and campus to be on. You're all lucky to be here, and I was lucky that you invited me here for the last 2 days. So let me close by saying thank you very, very much for the last 2 days. Okay.
Yeah. Do you have any ideas or any explanations for the donut hole in that map of chronic wasting disease, Iowa?
They haven't found it yet. That's my prediction. It's there. It's there. They just haven't found it yet. I can't imagine that Iowa is going to escape. Tom, do you have any comment?
That question, but I have a question.
Okay. I mean, that's my explanation. Actually, some of the Iowa soils, it takes a long time to weather things in Montmorillonite, so you generally don't get Montmorillonite behind the terminal moraine. Iowa is ahead of the terminal moraine. There's Montmorillonite in soils in Iowa.
And almost the entire state is tilled every year. I don't know if that affects the lifespan of the plant.
I don't know. It's a very good question. I mean, the behavior of prions in the soil is just a really interesting problem in soil ecology. I don't know if it would or not.
Sometimes I think it's useful to think about carrying capacity in a little different way, that it controls the slope of the relationship between the per capita rate of increase and population size. So it's the strength of the feedback, the strength of density dependence.
Right.
And so as in this case, what's happening is as K gets smaller, the strength of density dependence is going up. No, because it's a negative slope. As K goes down, the slope gets steeper.
That's right. That's right. Slope gets steeper.
And so, what does that mean in terms of what you're seeing here? That stronger feedback from density pushes the population, so stronger density dependence pushes the population into areas where the disease cannot invade. Why is that?
The deer die first.
The deer die first.
Yeah, that's right. Yeah, so there's a competing hazard there, right? And so
if you, this is not often done in ecology classes, but in my mathematical ecology class, I like to derive the logistic equation. And the way you derive the logistic equation is start with the exponential equation of population growth, e to the b minus d times t, and b and d are the birth rate and per capita birth rate. Well, here, let me put it up here. This is what results in the exponential equation. If you integrate that, you get n at time t equals n0 e to the b minus dt. And b is a per capita birth rate, d is per capita death rate. And we know populations don't grow exponentially for a long time. So what we want to do is say, well, maybe the per capita growth rate here is some basic per capita growth rate minus a density dependent term times the size of the population. So in other words, as population size goes up, per capita birth rate goes down from some nominal amount when the population is small, and the per capita death rate goes up. Let me make that a delta times n, like that. You take these terms, you put them back in here, and go through a lot of ugly algebra, and what you end up with is a combination of all these parameters where, what is it? It's B0 minus D0 over beta plus delta. That's what carrying capacity is. K is just a parameter substitution to clean up the equation because you don't want all this ugly stuff here. But what it is it's the ratio of the net per capita growth rate, births minus deaths when the population is low, to beta and delta. Those are the strengths of the density dependent factors. So to get K smaller, you make these bigger, which is what you were saying, right? Make the denominator bigger, K goes down. Well, if you make these things bigger, what is it saying? Is that the birth rate is going down steeper, right? So here's N and here's B, and the slope of that line is beta. here's D against N, this D, and the slope of that line here, that's my delta. So if these go up, increase, this goes down like this goes up like this, and you get greater density dependent regulation, but a smaller value of K. So the deer die early. The good die young. And if the deer are dying early, the susceptible deer never get the prion, and the prion doesn't get a chance to reproduce.
So putting the rubber to the road, if you were managing a deer herd and landscape in Iowa, would you intentionally reduce the carrying capacity? Or is this just academic ivory tower stuff and you wouldn't go out there to reduce your carrying capacity?
Well, if you want to solve the problem, I mean, look, this is just a model, okay?
But what would you do? What would you do?
I would stop trying to increase carrying capacity. And I would shoot a lot of deer. I'd reduce the size of my deer herd as much as I could get away with it politically.
Well, having been in that political argument before, the response of the policymaker is, this solution sounds like a lot worse than the problem.
That's right.
And in some ways, I mean,
Maybe it is. Yeah, but then you have to live with the problem.
yeah, and by and large, that's what's happening.
Yeah. I suspect that probably is what might end up happening in Minnesota. You're just a few years ahead of us. But right now, Minnesota's freaked out.
Minnesota's like that.
Yeah, no, we're
Michelle Bachmann, Jesse Ventura.
Well,
I mean, we could go on and on.
most Minnesotans are stable Lutherans, you know. Bachmann and Jesse Ventura are kind of aberrations.
Let's thank John one more time.
Now, there's one more question. Let's go.
Management approach fails to account for resource selection by a social animal.
Yeah,
The whole map, and you can kill half the herd, and they might just use half the space, but
Yeah.
still hang together. So it gets complex.
yeah, and the model gets complex, and obviously you got to get more complicated than this to be realistic. The problem then is you lose a lot of the power of mathematics. So there's always a trade-off in modeling between keeping models simple that you can understand them, and getting models so complicated that you don't understand them any better than the real world out there. So, yeah, it's a trade-off, but what it's at least doing is crystallizing what the problem is. Despite the fact that the model is simple and it's probably not realistic, my feeling is that these conclusions are going to be robust.
You've all heard the dangers of crystal math.
But the point is, we may be facing a point where we have to choose between high carrying capacity and disease. And you can have high carrying capacity and a healthy herd at the same time.
Thanks, John.